Hi. Good morning, everyone. My name is Mohammed Zain Mobeen. I'm a PhD student at the Copernicus Institute Center for Astrophysics in Torun, Poland, and I'll be sharing some of the work that we've done on V838 Monocerotis. So V838 Mon erupted back in 2002 in what is now known as a luminous red nova event. As the result of that was that its brightness went up by several orders of magnitude. It soon after peaking began to cool down. Its spectra changed from a type A to a late L-type supergiant. The spectra showed various molecular lines as well as atomic emission lines. And eventually, the source, after dropping off in luminosity, it started to brighten in the infrared, which was suggestive that dust formation had taken place. So V838 Mon currently is understood as the result of a stellar merger. So the hypothesis that was proposed by Tilinda and Noam Soker in 2006 was the stellar merger of a 0.3 solar mass YSO pre-main sequence object and an 8 solar mass B-type object, B-type star. And the merger was thought to have occurred due to the common envelope mechanism, in which you have these two stars in a binary. The more evolved star, its radius increases, it engulfs the companion, and because of that, the orbital radius begins to shrink, and that triggers an in-spiral, therefore causing a merger. We know as of now that this merger occurred in a hierarchical triple system. So the merger remnant is in a binary with another B-type star. And V838 Mon is not the only type of its kind. We know of a dozen or so more stellar merger candidates. In fact, for one of them, we've actually, there's photometric data that proves that the merger actually was observed. All right, so this is just a cartoon of what we have. We have the merger remnant, which is infrared bright, and it's separated by a distance of 230 AU from its B35 companion. And so the companion, as of now, is not visible in the optical, but it was eclipsed months after the outburst. So because of the infrared brightness, this is an ideal candidate for interferometry. And so we've mostly a sort of brief history of previous interferometric studies starts from 2005 when the now defunct PTI interferometer was used to measure the HK band size of V838 Mon. The next such study was done almost a decade later by Chestnut et al. In 2014. They used the median amber instruments to figure out so they found the data best explained by this elliptical elongated structure, and they also measured the size again, which suggested some contraction had taken place. Recently, ALMA was used to also study V838 Mon. This is work done by my supervisor, Tomasz Kamiński, in 2021. And so you can sort of see that the ALMA suggests this complex morphology also, which extends out to larger spatial scales. This work was significant because it was the first time that the B-type companion was. Is the audio all right? Okay. All right. So the B-type companion was directly observed, and its position was revised. All right. So for 2020, we had some MATISSE observations, and the goal was to do imaging, but unfortunately, because of the pandemic, we only obtained 4 nights of data, and out of those 4 nights, only 2 observing blocks were usable. Fortunately, it was with the large configuration, so we know we were getting the most extended or the best resolution. So we decided to geometrically model these L-band, the interferometric observables and the L-band. So on the top left, you have the squared visibilities. In the bottom right, you have the closure phases. And if you look at the visibilities, as you go towards longer spatial frequencies, you see the visibility drop to about 0.3. So that suggests that we are in fact resolving some part of the source. If you look at the closure phases, you can see some deviations from zero. So closure phases being a probe of symmetry. These slight deviations suggest that there are some asymmetries present in the system. So I modeled the visibilities and closure phases using LitPro, which is a JMMC software, and it was done in 3 ways. So the first approach was to just use an extended source, use a disk or a Gaussian. The second was use an extended source and a point source. So remember that in the geometry of the system, you have the merger remnant, the newly formed star, and it's enshrouded in dust. The last approach had to do with using another point source, and this was done because, well, as I stated earlier, you have this binary system of the merger remnant and this B-type companion. So we wanted to see if by any chance we could constrain the position of the B-type companion in this waveband. All right. So these are the results. This was published in late 2021 in ANA. And so if you look at the so the top panel is visibilities and the bottom panel for each plot is closure phases. The visibilities are well explained by all 3 modeling approaches. So the models are circular Gaussian and elliptical Gaussian, and the same for the disk. You can only, the asymmetries are only explained when you have those point sources, which is expected because you're adding an you're adding an asymmetry in the model. So the companion, the separation of the point source in the 2-point source model does not actually, it's many orders of magnitude less than the actual separation. So we conclude based off of that we're not in fact seeing the B-type companion. However, we are sensing some asymmetries, but it's difficult to say much just because we're limited by resolution. And so we would need full imaging to eventually figure this out. So here's an example of one of the extended component fits. So you have the stretch disk model on the left, and we were also able to accurately constrain its position angle and the flattening ratio or the ellipticity quite accurately with errors of less than 10%. And so on the right, we also did this sort of preliminary image reconstruction. We used the Vissard algorithm with the resolution of 0.3 milliarc seconds, and it supports what we see otherwise in our model image on the left. So the position angle is about -40 degrees. It's consistent with what's been observed before with ALMA and other instruments, and so we see the stable, long-lived feature that persists. And this is just a cartoon illustrating the morphology across wavelengths. All right, so jumping into the future, right now we have MATISSE. We have more MATISSE observations and a lot more gravity observations. And so we, with MATISSE, what we see is, well, this time around, we have not only the L band, but also the M band, which goes from 4.5 to 5 microns. And interestingly, in the spectra, we see this feature at 4.6 microns, which we identify to be CO, which is, the first time we've detected CO, and we're seeing it in this band. We've seen it before in the K band. So yeah, this is of course this is an ongoing work. So we'll model this and see what else comes up later on. All right, with gravity, you can see that there's an abundance of data. The UV plane is pretty filled up. The closure phases are also once again indicating asymmetry, and you can see that the visibility suggests that something is resolved. So we've decided to do some image reconstruction, and for that we use the Myra algorithm with a field of view of 10 milliarc seconds, a resolution element of 0.1 milliarc seconds. This is the image that we get. And so essentially, if you look closely, there's these 2 components. There's these arches or these arch-like features that you see further away from the center, and then you see this inner disc-like structure. And so this to us seems like it's evidence for outflows, bipolar outflows, which is something you expect to see in stellar mergers. It's suggested by simulations. We also see this in another stellar merger, remnant V838 Sagittarius. So yeah, so in summary, we see a stable disk-like feature in the L band. First time we've detected CO in the M band. The K band image in gravity suggests bipolar outflows, and also this inner disk-like structure. So remember, the K band is probing very closely to the central merger remnant. So in the future, we plan to use more imaging algorithms just to make sure that what we're seeing is in fact real and not just an artifact. We also have Chara data that's going to help us probe the sub-millimeter, sub-milli-arc second scales. And we also hope to get more MATISSE data so we can do full imaging in the LM bands. And with that, I will end my talk. Thank you so much for paying attention.
For this talk about this fascinating object, are there any questions from the audience first? There's a question there. Please state your name and affiliation once you get the mic.
Hi, Gail Schaefer from the Char Array. So it looked like on, I think when you showed the MATISSE model, it looked like the disk was oriented differently from the image reconstruction. Can you comment on that a little bit?
Sure, let me just pull it up. This slide?
Yeah, it looked
Okay.
like, yeah, it's a little different orientation from the image reconstruction.
Well, I mean, well, yeah, I mean, it's not identically the same, but roughly it's probing the northwestern direction. Of course, I didn't actually measure the angle, but because, let me see if the cursor, oh, okay, yeah. So, measured north through east, this is with respect to the semi-major axis, this is the angle that we're probing. So, I would say that it's if this is the larger dimension, then it's probably roughly the same, not identical, I guess. But yeah.
There's one question online. So again, from Jin Hake. He's curious about the uniqueness of the solution when you are doing the image reconstruction.
Oh, okay. Yeah. So far, so I guess I should make a disclaimer that this is all preliminary, but I also I've tried. So the way I did this reconstruction was by using starting with a randomly generated image. I noticed that even when I use some other morphologies, for example, if I start with a disk or a Gaussian, I almost certainly see something, this sort of disk-like feature. It might vary in its exact morphology, but you certainly see something that's going northeast, very close to the central source. Now, with regards to these outer, these what I call outflows, they sometimes, so there is some uncertainty. So, for example, in some reconstructions, I'll see this northern part and not the southern. So I mean, yeah, that's something that we plan to explore more by using more imaging algorithms, hopefully in the near future.
Thank you. Any more questions from the audience or online? If not, then let's thank Mohammed again. Thank you.